learn about the various aspects of NLP and AI model development. This course is suitable for existing and aspiring data scientists, machine learning engineers, deep learning engineers, and AI engineers. A basic knowledge of Python and PyTorch and an awareness of machine learning and neural networks would be an advantage, though not strictly required. After completing this course, you will be able to describe the fundamentals of language understanding, including converting words to features and document categorization prediction. You will also be able to explain the NLP models and techniques, including n-gram, word-to-vec, and sequence-to-sequence. In addition, you will use PyTorch to build, train, and implement the NLP models. In Module 1, you will learn how to use one-hot encoding, bag of words, embedding, and embedding bags to convert words to features. You will also learn how neural networks are used for document categorization prediction, training, and optimization. The module will give you insights into the applications of n-gram language models. Get hands-on with lab exercises. You will use PyTorch in the Jupyter environment to build and train a simple language model with a neural network. In Module 2, you will learn the types and features of word-to-vec embedding models. You will also get to know about the purpose of using sequence-to-sequence models in NLP and sequence transformation tasks. In addition, this module will take you through the process of evaluating the quality of the generated text. In hands-on lab exercises, you will develop and integrate pre-trained embedding models. The course has the right mix of content to facilitate learning. Videos are short and focused on the main topic. Readings provide detailed content primarily in text format. The labs provide the technical environment, detailed instructions, and code snippets that you can use to complete hands-on exercises. The practice and graded quizzes will help you apply what you learned and assess your knowledge. To get the most from your course, watch all videos. Complete the labs to practice your new skills. Attempt all quizzes. Let's get started on this exciting journey. To converting words to features. After watching this video, you'll be able to describe one-hot encoding and bag of words. You'll also be able to explain embeddings and embedding bags and describe how to use embedding and embedding bag in PyTorch. Consider you're developing a natural language processing or NLP application to classify email. You can categorize emails in various ways based on the presence of specific words, the frequency of words, or the contextual meaning of words in the email. To implement this functionality, it's essential to convert words to numerical features so that machine learning models can process the text. Let's explore the details. Consider the following sample sentences. I like cats. I hate dogs. I'm impartial to hippos. Sets of sentences, documents, or sequences are often termed a corpus or data set. Let's use a neural network to identify the subject, cat, dog, or hippo. The input needs to be translated into numbers the neural network can understand. One-hot encoding is a method used to convert categorical data into feature vectors that a neural network can understand. Consider a table with the first column representing the token index and the second column representing the token. The third column represents the one-hot encoded vector. The dimension of the vector corresponds to the number of words in the vocabulary, and the token index represents the element of each vector. The token I is represented with all elements set to 0 except for the one corresponding to I. This will be the feature X for the word I. The token like is represented in a similar way. You can observe a pattern. This will be the feature X for the word like. The token cats is represented in a similar way, and so on. You can represent each token in a document as a vector. How do you use these vectors to depict the entire document or sequence? The bag of words representation portrays a document as the aggregate or average of one-hot encoded vectors. For I like cats, you combine the one-hot vectors. You add the one-hot vectors for I, like, and cats. The X vector is the bag of words vector for I like cats. Let's look at embedding and embedding bags. Consider a neural network used to classify the previous sentences about cats, dogs, or hippos. You input the bag of words vector and select the output value with the highest association for cats. You'll understand how the embedding and embedding bag layers can effectively replace this initial linear layer. Let's look at the hidden layer. When we input the one-hot vector for the word cat, which has zeros everywhere except the 7th position, the activation in the hidden layer corresponds to the parameters of the 7th neuron. Instead of using a one-hot encoded vector, you can substitute it with the token index, in this instance 7. The output mirrors the one-hot vector. The layer that accepts this index is called the embedding layer, and its output is the embedding vector. The embedding weights are combined to form an embedding matrix. The number of columns is the embedding dimension. Each row represents a word. Embedding vectors generally have a lower dimensionality compared to one-hot encoded vectors. Reducing the dimensionality simplifies the computational requirements for the model. When you feed a bag of words vector to a neural network's hidden layer, the output is just the sum of the embeddings. It also helps to view embedding as a row in the embedding matrix, labeling them with the word they represent. This process entails summing up all the vectors from bag of words and multiplying the result with the embedding matrix. Instead of doing this, you can use an embedding bag layer. The input is simply the indexes for each token, and the output is the sum of word embeddings. Let's now look at how to use embeddings and embedding bag in PyTorch. First, you need the tokens. Initialize the tokenizer, iterator from the dataset, and vocabulary. The input_IDS function tokenizes and generates the indexes for each data sample. These indexes are stored in the list index, where each element in the list is the indexes for the different documents. You can initiate the embedding layer and specify the dimension size of the embeddings. Next, determine the count of unique tokens present in the vocabulary. Now create the embedding layer embeds using the nn.embedding constructor. You apply the embedding object. The input is the index for the phrase "I like cats" to retrieve the embedding. What you'll see is a PyTorch tensor representation. Each row in this tensor aligns with the respective embedding for the words "I like" and "cats." You can retrieve the embedding for the last data sample, "I'm impartial to hippos," using its index. The result is a PyTorch tensor. Each row corresponds to the embedding for each tensor word. Initializing the embedding bag layer is almost the same as the embedding layer. Let's output the embedding bag for the first document. Using its index, you can access the embedding for "I like cats." The outcome is a PyTorch tensor representing the sum of average of all embeddings. For one sample, the offset parameter is always 0. Let's explore the offset parameter. In NLP, datasets are often represented as one-dimensional tensors. However, when working with embedding bags and other applications, it's crucial to identify the position of each document. Let's dive into this with our sample dataset. You combine the tensors of individual documents using the cat function with the index setting. The offset parameter captures the starting position of every document. You can count the tokens in each sample. This step helps in pinpointing the initial position. Using the cumulative sum method, you can accumulate the lengths, thereby determining the starting position of each sequence. You use the embedding bag function along with the offset parameter as with the index tensor. The result is the embedding bag. For each individual document, you have the average of its words embeddings. Let's now recap what you learned. In this video, you learned about one-hot encoding, bag of words, embedding, and embedding bags. One-hot encoding converts categorical data into feature vectors. The bag of words representation portrays a document as the aggregate or average of one-hot encoded vectors. When you feed a bag of words vector to a neural network's hidden layer, the output is the sum of the embeddings. The embedding and embedding bag classes are used to implement embedding and embedding bags in PyTorch. Welcome to Document Categorization Prediction with Torch Text. A document classifier seamlessly categorizes articles by analyzing the text content. As demonstrated, you simply feed in the raw text, and the system efficiently outputs the document's classification, whether it's science and technology, sports, business, or any other class. After watching this video, you'll be able to explain what neural networks are and describe basic neural network hyperparameters. You'll also create a neural network in PyTorch. First, let's do a quick recap of neural networks, where you'll mainly concentrate on understanding the inputs and outputs. A neural network is a mathematical function consisting of a sequence of matrix multiplications with a variety of other functions. It begins with an input layer. For instance, consider a bag of words vector. In this layer, you'll perform matrix multiplication, occasionally adding a bias. This constitutes the hidden layer. If the input employs a bag of words, this layer is known as the embedding layer, and its output is referred to as the logits. Subsequently, apply an activation function to each logit, a process known as activation, where each element is called a neuron. Sometimes an activation function or bias addition is not applied to embedding layers. The operation is then repeated. Another matrix multiplication is performed, and once again, each resulting element is termed a neuron. Through this iterative process, the input data is transformed step by step, enabling the network to learn classification. The parameters that the network adjusts during training are known as learnable parameters. In the article, ESPN's varied football coverage input an embedding vector into the network. For each category, the neural network outputs a vector of logits, where each logit is a score reflecting the article's likelihood of fitting a particular news category, as shown here. The associated table links vector elements to categories. World is first, followed by sports, business, and science and technology. To determine the class of an article, you're going to input the logits from the output layer into the argmax function. The argmax function identifies the index of the highest logit value, corresponding to the most likely class. Here, the argmax function selects index 1, which has the highest logit value of 7. This indicates that the network classifies the article as belonging to the category associated with index 1. This corresponds to the article class of sports. This graph illustrates the architecture of a neural network. Each circle represents a neuron. Starting from the left, each neuron in the first box corresponds to an element in the input vector or input layer, and the connecting lines represent the weight matrix. The neurons at each subsequent level signify the components of the hidden and output layers. After processing through an activation function, obtain the hidden layer values denoted as Z. The final layer's connections embody the weights leading to the output, with each neuron reflecting one of the 4 output classes: world, sports, business, and science and technology. After that, use argmax to find the class with the highest score. Now let's learn about the neural network hyperparameters. These are externally set configurations of a neural network. The architecture can vary in the number of hidden layers. For example, the network depicted at the top has a single hidden layer, while the one at the bottom features 2 hidden layers, with each feeding into the subsequent one. Don't forget that the input layer is just the input vector, so your focus will usually be on architectures with 1 hidden layer. You could adjust the number of neurons in each layer. For instance, in the network depicted above, the second hidden layer consists of 5 neurons, whereas the bottom network contains 4. Furthermore, if the first hidden layer functions as an embedding layer, then the number of neurons corresponds to the vocabulary size. The number of neurons in the output layer always equals the number of classes. Both number layers and neurons can be selected via the empirical validation data. Now let's create a neural network in PyTorch. You will use the ag-news dataset using torch text. The output consists of text representing news articles along with their corresponding labels indicating their categories. You'll display the label and the news text in a table. Then use a Python dictionary to assign the appropriate category headlines to the labels. The news categories are displayed: business for the first 2 sentences and science and technology for the last sentence. Let's build the standard text processing pipeline. You should tweak your function so that label numbering begins at 0. Now you'll set up a batch function for embedding bags and add code to append the labels for each sample to a batch. Next, you'll create a data loader with a batch size of 3. Let's explore the sample. Here you have 3 labels for each sample. Next are the token indices, which form the basis for your bag of words model. Finally, observe the relative positions of these indices, which are essential for constructing the bag of words model. The model's architecture features 2 primary layers defined in the constructor. The first is the embedding bag layer, followed by the fully connected layer. The initialization of weights is also done. During the forward pass, you'll input text and offset it into the embedding bag without applying the activation, which then feeds into the fully connected layer for the final output. Now, create an instance of the text classification model with specified vocabulary size, vocab size, embedding dimension, M size, and the number of output classes, num class. Now make a prediction using the text indices and the offsets and assign it predicted label. First up, you're looking at the logit values. In PyTorch, each row represents a different sample. Columns correspond to the logit values for each class. Unlike the earlier row vector example, it's organized by columns here. You'll then apply the argmax function across each row. This identifies the maximum value in each row. The position of this maximum value indicates the predicted class for samples 0, 1, and 2. The prediction function works on real text that starts by taking in tokenized text. It processes the text through the pipeline, and the model predicts the category. The label with the highest output value is then returned as the predicted category. When you apply the function, the article gets classified under sports. Trying this in the lab might yield a different result since the model hasn't been trained yet. Let's now recap what you learned. In this video, you learned that a document classifier seamlessly categorizes articles by analyzing the text content. A neural network is a mathematical function consisting of a sequence of matrix multiplications with a variety of other functions. The argmax function identifies the index of the highest logit value corresponding to the most likely class. Hyperparameters are externally set configurations of a neural network. The prediction function works on real text that starts by taking in tokenized text. It processes the text through the pipeline and the model predicts the category. Welcome to training the model in PyTorch. After watching this video, you'll be able to describe how to train a neural network in PyTorch. Let's use concepts related to cross-entropy loss and optimization to train the model with PyTorch. Consider you have a news data set that has been tokenized and indexed. Let's proceed to split the data set. Create 2 iterators for the AG News dataset, where one contains only training. Further, split the training data into training and validation. After splitting, data loaders are set up for training, validation, and testing. Batch size specifies the sample count for gradient approximation, and shuffling the data promotes better optimization. These are the codes that you can use to define your model. When you do so, init weights helps with optimization. This code creates an instance of the text classification model. Now you initialize your optimizer and loss function and then set the number of epochs during which you'll record the loss and accuracy for each epoch. To train your loop, iterate over each epoch, that is, each time you pass through the entire data set. Set the model to training mode and iteratively calculate the total loss. Divide the data set into batches, which improves performance. Perform gradient descent to adjust the model parameters. Finally, update the loss after each batch is processed. For each epoch, record the loss and accuracy. If the model achieves higher accuracy on the validation dataset, you can save its parameters. As you plot the loss and accuracy over time, you can observe a trend. As the loss decreases, accuracy correspondingly increases. Let's now recap what you learned. In this video, you learned that the training data is split into training and validation, and then data loaders are set up for training, validation, and testing. Batch size specifies the sample count for gradient approximation, and shuffling the data promotes better optimization. When you define your model, init weights helps with optimization. To train your loop, iterate over each epoch. Set the model to training mode, and iteratively calculate the total loss. Divide the dataset into batches, perform gradient descent, and finally, update the loss after each batch is processed. Welcome to Language Modeling with N-grams. After watching this video, you will be able to explain the concept of bigram and trigram models. You will also be able to describe and illustrate language modeling with N-grams. Let's begin with understanding about N-grams. Consider the phrases I like and I hate. How would you complete these sentences? For instance, if you were given I like followed by a blank, would you choose surgery or vacation? Most people would likely complete it with vacation upon seeing the word like. Similarly, with the phrase I hate followed by a blank, the expected completion is surgery, reflecting common associations with these words. These examples demonstrate how your word choices are often influenced by the context provided by preceding words. Consider the phrase, I like vacations, which can be represented as a sequence. You can depict this using a table, with each column labeled omega 1 to 3, representing a word and the subscript indicating its position in the sentence, that is, word 1, word 2, and word 3. The same goes for I hate surgery. This is where the bigram model comes into play. It's a conditional probability model. What's the probability of your third word, word 3, given the second one, word 2? Word 2 represents your context, the second word, which is crucial in guiding the prediction. In a bigram model, your context size is 1, meaning you'll consider only the immediate previous word to predict the next one. Given the second word is like, that is, word 2 equals like, what could the third word be? Using the table, count the occurrences of each potential follow-up to like in the third column. By examining the table, observe that surgery never follows like. Hence, the probability of word 3 being surgery is 0. However, vacation appears after like, and the probability of word 3 being vacation is 1. Consider the phrases surgeons like surgery and I hate surgery. Adding surgeons changes the context of the sentence, making it at least plausible that surgeons like surgery. Let's create the same table. The trigram model is also a conditional probability function and can improve on the bigram model's limitations by increasing the context size to 2. Now, in addition to word 2, you also use word 1 to predict word 3. Let's examine the probability of word 3 equaling surgery. Given that word 1 is I and word 2 is like, you will find that the probability is 0. However, if you change word 1 to surgeons, the probability of word 3 being surgery is now 1. Consider the phrases surgeons like surgery, I hate surgery, and I like vacations. How would you complete the phrase surgeons like? You can employ the trigram model to predict the next word by leveraging the probabilities generated from the table. For context, set the first word to surgeons and the second to like. To predict the third word, denoted as omega, identify which word maximizes the likelihood of being the third word. This optimization is achieved using the argmax function, which selects the word with the highest probability from the different possible third words given that the first word is surgeons and the second is like. As illustrated, all possible outcomes for the third word have a probability of 0, except for surgery. Therefore, the predicted third word is surgery. Let's consider predicting the next word, word 3, given that the first word is I and the second word is like. If instead you're aiming to predict a word at some arbitrary point t, using the preceding points t1 and t2, and if you're assuming these relationships remain constant over time, that is, implying stationarity, then you can apply the trigram or bigram models at any point in time. For the trigram case, you can use words at positions t2 and t1 to predict the word at position t, following the same predictive process. You can generalize the concept of a trigram to an n-gram model, which allows for an arbitrary context size. In this expanded framework, t denotes the chosen context size. However, calculating the probabilities for larger context sizes can become increasingly complex. Fortunately, neural networks offer a solution by approximating these probabilities. Specifically, apply the softmax function to estimate the probabilities and then train a neural network to predict the next word based on the previous words. The context word is used as a feature, that is, the context vector to define the previous words. Let's revisit the previous example where each word in your vocabulary of 6 words, that is, I, hate, like, surgeons, surgery, vacations, is represented by a 6-dimensional, one-hot encoded vector. Consider encoding the phrase, I like, with a context size of 2. If you employed a bag of words model, the vector representation of I like would be identical to that of like I. To establish the concatenate vector, concentrate the individual vectors corresponding to each word as illustrated here. Instead of performing the operation on raw one-hot vectors, concatenate the one-hot encoded embedding vectors. In the realm of neural networks, the context vector is generally defined as the product of your context size and the size of your vocabulary. Typically, this vector is not computed directly. Instead, you should construct it by concatenating the embedding vectors. Let's examine the neural network architecture for an n-gram model. Imagine you're working with a small problem, a 6-word vocabulary, and a 2-word context. Recall the neural classifier designed to categorize one of 4 articles, which has 4 output neurons. However, the network must predict one of 6 possible outputs, one for each word in the vocabulary, so there are 6 neurons in the output layer. Given the context size of 2, adjust the input accordingly. The input dimension is the product of vocabulary size and context size. With 6 words and a context size of 2, your input dimension is 12. Utilize the final layer's output directly, without needing to convert it to probabilities. This feed-forward neural network ignores the dependence on T, as it does not have a built-in mechanism to capture the order or position of words in a sentence like recent neural networks that work better at generating text. Let's now recap what you learned. In this video, you learned that a bigram model is a conditional probability model with context size 1. That is, you consider only the immediate previous word to predict the next one. A trigram model is also a conditional probability function and can improve on the bigram model's limitations by increasing the context size to 2. The concept of a trigram can be generalized to an n-gram model, which allows for an arbitrary context size. In the realm of neural networks, the context vector is generally defined as the product of your context size and the size of your vocabulary. Typically, this vector is not computed directly, but is constructed by concatenating the embedding vectors. Welcome to N-grams as neural networks with PyTorch. After watching this video, you will be able to create an n-gram model in PyTorch and train it. You will also be able to use n-grams as neural networks with PyTorch. In PyTorch, you can create an embedding layer with an arbitrary vocabulary size and set the embedding dimension and a context size of 2. The next layer's input dimension must be the product of this context vector embedding dimension and the context size. Start with 2 indices, representing the input context size of 2. These 2 samples are used as input for the embedding layer. The output is 2 embedding vectors of dimension 3. Use the method reshape to reshape the embeddings to form the context vector, which is the context size or number of samples multiplied by the embedding dimension. This concatenates all the samples together. This is used as an input to the next layer. In PyTorch, the n-gram language model is essentially a classification model, using the context vector and an extra hidden layer to enhance performance. The n-gram model predicts words surrounding a target by incrementally shifting what's known as a sliding window. In a bigram model, the prediction for words at position t is based on the positions t1 and t2. Beginning at t equals 3 to preclude negative indices, each table row represents a distinct t-value that aligns with the word's position. Column 2 displays the context, and column 3 shows the predicted word, both dependent on row t. Consider the phrase, "I like vacations," with each word's index beneath it. For t equals 3, the context is "I like," shown in blue, and the predicted target word is vacations in red. Moving to t equals 4, presented in row 2, the context updates to "like vacations" with "and" as the next prediction. This method is applied throughout the entire sequence. In PyTorch, for n-gram modeling, implement windowing to create batches of context and target words. It initiates the process where targets and contexts are generated using a batch function. A for loop iterates from the start of the context size, which in this example begins at 2, marking vacation as your initial target within the window. I is the target index. The context is gathered by subtracting j from I. Then slide the window forward, incrementing I to capture successive targets and contexts for the entire sequence. Here, you are going to create a toy data set. Now, you'll create a pipeline that converts the text to indexes. Instead of using a data set object, you will use a list object. In training the model, prioritize the loss over accuracy as your key performance indicator. Train the model similarly to your classification model by padding tokens to ensure consistent shape. Here, you will pad with previous values for alignment. The index-to-token attribute obtained via vocab getItOS is a list where each element corresponds to a word, and the index within the list corresponds to that word's token index. This list serves as a mapping to translate the numerical output of a neural network, which could represent class or token indices, back into a human-readable format, essentially acting as a decoder. Thus, when a neural network predicts an index, this list can be used to retrieve the associated word. Let's make a prediction. Apply a text processing pipeline to the string never gonna. The result is the list 3, 1, which represents the token indices. Convert the list of token indices into a PyTorch tensor. Make a prediction with the model and select the index with the largest value. Finally, convert the index to a token using the index-to-token mapping. You can use this function to generate a sequence of words using a model. Let's now recap what you learned. In this video, you learned that an n-gram model allows for an arbitrary context size. In PyTorch, the n-gram language model is essentially a classification model, using the context vector and an extra hidden layer to enhance performance. The n-gram model predicts words surrounding a target by incrementally shifting as a sliding window. In training the model, prioritize the loss over accuracy as your key performance indicator or KPI. Welcome to Word2Vec, Introduction and SIBO Models. After watching this video, you'll be able to explain the concept of Word2Vec and describe Word2Vec's continuous bag of words or SIBO model. You will also learn to create a SIBO model. So what is Word2Vec? It is the short form for word-to-vector. It is a group of models that produce word embeddings or vectors, which are numerical representations capturing the essence of words. For example, king is closer to man and queen to woman due to their similar meanings. Interestingly, subtracting man from king yields a vector similar to queen, illustrating the effectiveness of these embeddings in capturing word relationships. These vectors can be utilized in natural language processing or NLP tasks to enhance performance by substituting the randomly generated embeddings. To acquire these vectors, you can begin with randomly generated embeddings. You can use a neural network model consisting of an input layer, an embedding layer, and an output layer. Words are fed into an embedding layer, which interacts with a softmax output layer to predict context words. Training involves tuning the W, hidden layer, and W', output layer weights to refine word vector representations. The number of neurons in both input and output layers corresponds to the vocabulary size, while the embedding layer's size, which is chosen by the user, defines the word vector dimensions. After training the neural network, if the network predicts queen following woman with a higher probability than it does for man, the embedding for queen will be closer to woman than to man. Similarly, if king is probabilistically more associated with man than with woman, the resulting vector for king is closer to man than woman. Now, let's use the network to attempt to predict words from the given window using other words within the window. Set the window width to 1. At t=1, exercises is the target word, with she and every as context words. At t=2, every becomes the target, surrounded by exercises and morning in context. For the context and target words with a window width of 1, the context includes the word at t-1 and t+1. The target word is at t. At t=1, the context consists of she and every. The target word is exercises. As you move to t=2, the context includes exercises, morning, and the target word is every. Next, you will learn about the continuous bag of words or SIBO model. This model utilizes context words to predict a target word and generate its embedding. In the table shown, the second column lists the predicted word from the network. When she and every are given as inputs, the model predicts exercises. With exercises and morning as inputs, the model predicts every. In the SIBO model for the sentence, she exercises every morning, the input dimension of 4 matches the number of unique words in the corpus. The goal is to predict word likelihood, so the output dimension is also 4. The target word is exercises, with context words she and every combined into a bag of words vector. This vector passes through the hidden layer containing word embeddings. In the output layer, expect the highest logit value for exercises, indicating the model's prediction for this context. Now, let's shift the context window to consider new inputs. The words exercises and morning are encoded as one-hot vectors and provided as inputs to the model. During training, your goal should be to fine-tune the model's weights so that it effectively predicts the target word every, which should correspond to the highest logit value in the output layer. To create the SIBO model, first you will initialize it. Then you will define the embedding layer using NN embedding bag, which calculates the average of context word embeddings. You will also configure the fully connected layer using self.fc with input size embeddim and output size vocab size. In the forward method, you will pass input text and offsets through the embedding layer, which retrieves context word embeddings and calculates their average. Next, you will apply the rel-u activation function. Afterward, the output of the rel-u activation goes through the fully connected layer. Finally, you will create an instance of the SIBO model. Next, you will initialize the tokenizer using steps 1 and 2. Using step 3, you will create a vocabulary from tokenized data. In step 4, you will set the context size to 2. Then you will slide over the text to form context target pairs. Next, using step 5, you will set up a text processing pipeline, a data loader, and a batch function for a network. It will have a bag of words of batch size 64 to prepare batches for training on next word prediction tasks. Let's now recap what you learned. In this video, you learned that word-to-vec is the short form for word-to-vector. It is a group of models that produce word embeddings or vectors, which are numerical representations capturing the essence of words. A neural network model consists of an input layer, an embedding layer, and an output layer. Words are fed into an embedding layer, which interacts with an output layer to predict context words. The number of neurons in both input and output layers corresponds to the vocabulary size, while the embedding layer's size, which is chosen by the user, defines the word vector dimensions. The continuous bag of words, or CBO model, utilizes context words to predict a target word and generates its embedding. Welcome to Word2Vec, skipgram and pre-trained models. After watching this video, you will be able to describe Word2Vec's skipgram model, create a skipgram model in PyTorch and train it, and explain large pre-trained embedding models. A skipgram model is a reverse of the continuous bag of words, or CBO model. It predicts surrounding context words from a specific target word. For instance, it aims to forecast words t-1 and t+1 for a given target word t. At t=1, with exercises as the target, the model predicts she and every. At t=2, when every is the target, it aims to predict exercises and day. The terminology may be confusing as the target is not the dependent variable. In this depiction, exercises is the selected target word, encoded as a one-hot vector within the vocabulary space, marked by a 1 for exercises and zeros for all other terms. The output layer is tasked with predicting the surrounding context words, she and every. Ideally, after training, the model's output for each context position should have the highest logit values for the actual context words. The skipgram model simplifies the task by predicting one context word at a time from a target word. For example, for t=1 with exercises as the target, it predicts the preceding context word, she. Independently, it predicts the following context word, every. This makes the complex context prediction easier by breaking it into smaller, manageable tasks. Now, let's examine the neural network. At the input, you have one hot encoded vector for exercises, and the prediction is she. The second pair is exercises and every. Let's take a look at the skipgram model in PyTorch. To create a skipgram model, first, you will initialize it. Then you will define the embeddings layer using NN embedding, which creates word embeddings for the given vocabulary size and embedding dimension. FC layer is a fully connected layer with an input dimension, or embed dim, and an output dimension of vocab size. In the forward method, the input text is passed through the embeddings layer to obtain word embeddings. Next, you will apply activation and linear layers. Finally, you will create an instance of the skipgram model. The sequence generation function is identical to CBO, but with a switch in the order of the target and context. This breakdown allows you to work with the full context in smaller parts. The code segment breaks the context into smaller, manageable segments. Let's now look at the first sample in the code snippet. Each sample consists of two elements, the target word and its context. The nested loop iterates through the context, that is, the second element of the sample, and appends each part to the target. This results in the original full context being segmented into smaller, discrete parts. Next, you will flatten the data. The collate function is similar to the CBO model. You will then create a data loader object. Let's examine a single batch from the data loader you have created. The tensors are returned, including the target and context. You can also observe the indices. Additionally, the tokens are displayed here, which makes it quite intuitive. To train the parameters, you will define the learning rate and loss function cross-entropy loss criterion. The optimizer optimizes the parameters of the model, which are obtained by model CBO parameters. For the skipgram model, you only need to change the input object of the optimizer. Then you will define a learning rate scheduler. Now let's define the training function to train the model for a specified number of epochs. You must include a condition to check whether the input is for skipgram or SIBO. The output of this function includes the trained model and a list of average losses for each epoch. Now to retrieve word embeddings, you will call the train function with the data loader you created for training the SIBO model. Once the model is trained, you can retrieve the weights, which are the actual word embeddings. You can get the embedding vector for a specific word by its index. Now you will learn about text classification using pre-trained word embeddings. Word embeddings utilize Stanford's pre-trained GLOVE or global vectors that leverage large-scale data for word embeddings. Using a different method, it can be integrated into PyTorch via torchtext.vocab for improved NLP tasks such as classification. You will initialize GLOVE with GLOVE within parentheses name equals within single quotes 6b to load pre-trained vectors and create a custom vocab object to match different tokens. You've developed a text classification model and integrated GLOVE word embeddings into a PyTorch layer. You use .from pretrained with GLOVE vectors 6b .vectors. You will create a word amending bag operation. You can also try setting freeze to false if you have a larger data set. That's it. Check out the lab for more. Let's now recap what you learned. In this video, you learned that skipgram model predicts surrounding context words from a specific target word. It operates in contrast to the SIBO model. The skipgram model simplifies the task by predicting one context word at a time from a target word. The sequence generation function in the creation of the skipgram model is identical to SIBO, but with a switch in the order of the target and context. This breakdown allows you to work with the full context in smaller parts. While training the parameters, you define the learning rate, loss function, optimizer, and learning rate scheduler. Once the model is trained, you can retrieve the weights, which are the actual word embeddings. Word embeddings utilize Stanford pre-trained GLOVE or global vectors that leverage large-scale data for word embeddings. Welcome to the Introduction to Sequence Models and Recurrent Neural Networks. After watching this video, you'll be able to explain sequence-to-sequence models and how they have revolutionized various natural language processing tasks, such as machine translation, text summarization, and chatbots. You'll also be able to describe basic recurrent neural networks, or RNNs, and how sequence-to-sequence models employ RNNs to process variable length input sequences and generate variable length output sequences. Sequence-to-sequence models within generative AI are used in machine translation, such as converting English phrases into French. Chatbots transform your queries into conversational responses, while summarization algorithms condense extensive texts into concise summaries. With code generation, you describe your task, and the AI generates the appropriate code. Sequence-to-sequence models process multiple inputs, here illustrated by 5 embedding vectors labeled x1 to x5, corresponding to time units. The outputs marked y1 to y5 typically represent tokens but can vary widely with many applications. Notably, input and output sequences need not be of equal length. For instance, sequence-to-label tasks take multiple inputs to produce a single label, useful in document classification. Conversely, label-to-sequence tasks generate a full sequence from a single input, as seen in generative models for image creation. Context is vital for accurately interpreting language. Take the sentences, "The man bites the dog," and "The dog bites the man." While a bag of words model cannot differentiate between them, treating them as similar due to identical word frequencies, sequence representation through one-hot encoded words, or embeddings captures their distinct meanings. The difference is highlighted in red, illustrating how such representations enable a more precise understanding of context. Neural networks typically operate under the assumption that each sample is independent and identically distributed, or IID. To illustrate, imagine drawing a ball labeled with variable yt from an urn multiple times. If each draw is independent and the urn's contents are unchanged, the t is redundant, and the probability distribution remains constant, fulfilling the IID assumption. However, Consider the scenario where the balls are not replaced after each draw. In this case, the probability for y at t equals 1 is 1/10, but the probability at t equals 2 depends on the previous draw at t equals 1. This necessitates adjusting the probability distribution after each draw. Leading to the concept of conditional distributions, the model needs memory. Therefore, you require a model that can account for this dependency using models that have memory. In sequence model training, you'll refine your data, starting with a collection of sentences punctuated by BOS and EOS tags to denote beginnings and ends. This clear demarcation helps the model recognize start and stop points within a sequence. Next, sort the sentences by length to batch together those of similar size, which streamlines the learning process. PyTorch, like other frameworks, requires consistent batch sizes. Therefore, you should append pad symbols to the shorter sentences to equalize their lengths with the rest. Now, you'll learn about recurrent neural networks, or RNN. It is a type of artificial neural network that uses sequential or time series data. As its name suggests, RNN is designed to remember past information and use it to influence future decisions. Let's explore how a simple RNN operates. First, look at the input layer, labeled as XT. This is where your RNN receives data at each specific time step. It's akin to receiving a new puzzle piece at every moment. Next, you have the heart of your RNN, the hidden state, denoted as HT. Think of it as the network's memory, where you will apply an activation function, usually a tanh. It captures and retains information from all the previous inputs. This is crucial because it allows the network to remember and consider past data while processing the current input. Now observe how the hidden state and the current input combine. In some RNNs, they're concatenated, forming a larger set of data for processing in what is also called the concatenated layer. This is critical for understanding the network's ability to connect past and present information. Let's move to the output, represented by ZT. This is what the RNN calculates at each time step, based on the current input and what it has remembered in its hidden state. This is where the context is stored. This process is similar to a regular neural network. For the classification problem, you can simply obtain the maximum value and use RNNs in hat Y in language modeling to predict the word omega hat. This method is called greedy, decoding where the model picks the highest score token and returns it as its prediction. Please note that top K sampling strategies seem to produce more fluent text than the traditional greedy method. Let's unroll the RNN over time. Start with the initial hidden state, that is, a vector of zeros. Then, with each input, XT, the RNN updates its hidden state, HT, and produces the output hat, YT. For the next iteration, introduce a new input, XT, and the network utilizes the hidden state from the first time step, learning from the past to inform the future. And then the process repeats. To output a sequence hat YT, you sometimes need to use only the hidden state, or you can even use the last hidden state, HT, as an input to another RNN. RNNs only remember short-term information and are challenging to train. Two popular RNN enhancements are gated recurrent units, or GRUs, and long short-term memory, or LSTMs. In a GRU, there are two gates, the reset R and the update Z. The update gate determines the proportion of the previous hidden state to carry forward, while the reset gate decides how much of the previous hidden state to disregard. Working together, they update the hidden state and control the flow of information over time. Finally, another activation function is applied before the model makes a prediction. The LSTM cell comprises the input gate, the forget gate, and the output gate. LSTMs extend a network's memory, complementing short-term with long-term recall. They selectively retain and transport crucial data through time. The diagram shows H as short-term memory, discerning what's important. It selectively filters specific information from C that is pertinent to the current time step. Conversely, C preserves the full scope of the memory to be conveyed to subsequent time steps. Let's now recap what you learned. In this video, you learned that Sequence-to-sequence models within generative AI are used in machine translation, such as converting English phrases into French. Sequence-to-label tasks take multiple inputs to produce a single label, useful in document classification. Label-to-sequence tasks generate a full sequence from a single input, as seen in generative models for image creation. RNN is a type of artificial neural network that uses sequential or time series data. It is designed to remember past information and use it to influence future decisions. RNNs only remember short-term information and are challenging to train. Two popular RNN enhancements are gated recurrent units, or GRUs, and long short-term memory, or LSTMs. Welcome to Encoder-Decoder RNN models, training and inference. After watching this video, you will be able to use a translation dataset in PyTorch to train and infer an encoder-decoder RNN-based model. You'll be working with the multi-30K dataset, which includes training, validation, and test sets of English to German text. Before delving into implementing the sequence-to-sequence or seek-to-seek model, let's review how to load data in batches for training models using PyTorch's data loader. A .py file has been created that fetches the multi-30K dataset. The collation, that is, tokenization, numericalization, and addition of beginning of sequence, or BOS, end of sequence, or EOS, and padding have also been done. You will also see the created iterable batches of SRC and TRG tensors. As a first step, you must download and run the .py file. Then call the getTranslationDataLoaders function with an arbitrary batch size to create the data loaders for training and validation. You can also check a data sample. In general, sequence-to-sequence models are more difficult to train than RNNs, and several factors come into play. However, typically the aim is to minimize the cross-entropy loss by summoning the output of the predicted outcomes with the actual labels. Let's use blue to denote a correct prediction. The procedure for training sequence-to-sequence models has almost similar steps, but let's highlight similar differences from neural networks. First, initialize the model in training mode to activate essential layers like dropout, ensuring optimal performance during training. Iterate through training data batches, assign input, SRC, and target, TRG, sequences to the correct device, and generate predictions by output. For sequence models, like RNNs, where the input shape often differs from other model types, it's crucial to reshape the output's tensor too. Here, target length 1 represents the rows excluding the initial BOS, or beginning of sequence token, ensuring you don't include it in loss computation. Batch size is the columns, each representing a separate sequence in the batch, and output dimension corresponds to the columns representing the predicted output for each token in the sequence. This reshaping aligns the rows and columns correctly for loss calculation, matching the output predictions to the target dimensions. Finally, you can calculate the average loss per batch after processing all batches. You will also create an evaluate function that is identical to the training function, but you must use different data and set the model to eval to speed it up. Let's see how to make a prediction. Performing translations in sequence models requires a more complex function for making predictions. The function takes a model, a source sentence, a target language vocabulary, and a maximum translation length. Firstly, convert the source sentence to the correct format, then feed it into the model's encoder to obtain hidden and cell states. Start the target tensor with the BOS token to initialize the translation and reshape it. To generate the translation, iterate up to max len. Utilize the last target tensor and the previous states in the decoder to obtain new outputs and states. Then choose the next token with the highest probability. Add it to the translation and store it. End the process if the EOS token appears, else feed the output to the input. Finally, convert token indices to words. Remove special tokens and concatenate the tokens to form the translated sentence. Now you're ready to run all the functions in the lab. Let's now recap what you learned. In this video, you learned that, in general, sequence-to-sequence models are more difficult to train than RNNs due to several factors. In model training, the aim is to minimize the cross-entropy loss by summing the output of the predicted outcomes with the actual labels. The procedure for training sequence-to-sequence models includes initializing the model in training mode to activate essential layers like dropout, ensuring optimal performance during training, iterating through training data batches, assigning input SRC and target TRG sequences to the correct device, and generating predictions by output, reshaping the output's tensor, which aligns the rows and columns correctly for loss calculation, and finally calculating the average loss per batch after processing all batches. Performing translations in sequence models requires complex functions for making predictions. Welcome to Encoder-Decoder RNN Models. Translation. After watching this video, you will be able to implement an encoder-decoder RNN model. Let's learn about the encoder-decoder architecture. As you know, RNNs can be used to create sequence-to-sequence models that receive sequence X as input and generate sequence Y as output. Note that X and Y do not necessarily need to be of the same length. For this purpose, encoder-decoder architectures are introduced. A popular example of a sequence-to-sequence model is a translation model. Let's check an actual example to see how encoder-decoder RNNs generate translation. The encoder-decoder sequence-to-sequence model works together to transform an input sequence into an output sequence. Encoder is a series of RNNs that process the input sequence individually, passing their hidden states to their next RNN. The last hidden state, context, is passed to the decoder module. The decoder module, similarly, is a series of RNNs that auto-regressively generates the translation as one token at a time. Each generated token goes back into the next RNN along with the hidden state to generate the next token of the output sequence until the end token is generated. As RNNs become more complex, you can abstract away the finer details. Here, an RNN is represented with an RNN cell. The key distinction here is that the output from the previous state is recycled as input for the next state. For the encoder, the interest lies only in the hidden state and to not use the output. This is because only the decoder will generate the output text. The encoder is only responsible for encoding the input sequence. Now that you have an understanding of the overall architecture, let's delve into the internals of the encoder units. The encoder consists of multiple encoder units, each responsible for processing input tokens. At the heart of each unit is an embedding layer, which transforms the input token into an embedded vector. These vectors then traverse through the RNN cell to produce the hidden state, which is subsequently handed over to the RNN cell of the next encoder unit. To build an encoder in PyTorch, define a class inheriting from torch.nn.modules similar to a standard neural network. The embedding vectors serve as input to a long short-term memory, or LSTM, layer characterized by n layers, that is, the number of recurrent layers, and hiddim, that is, the size of the hidden and cell states. Incorporate dropout as an optimization technique to enhance performance. In the LSTM layer, input embeddings are transformed into hidden states and cell states, with hiddim specifying the number of neurons. During the forward method execution, the embedding layer processes the input, and the LSTM layer outputs the hidden and cell states. Only these states are retained. The output vector is discarded since it's not required by the encoder. Remember, unlike gated recurrent units, or GRUs, which have only hidden states, LSTMs maintain an additional cell state for each layer. The decoder is also composed of many decoder units within which the predicted token is generated. Each unit has an embedding layer, where embedded vectors are created. These vectors then pass through the RNN cell to output the updated hidden state, which will be passed to the RNN cell of the subsequent decoder unit. Next, a linear layer maps the RNN output to the output dimension to generate the next token. As you can see, the decoder works a bit differently from the encoder in the way that it receives its previously generated token and generates the next token auto-regressively. To build a decoder in PyTorch, create a decoder class, which is a subclass of NN module, serving as the base class for neural network modules. In the constructor init method, the decoder's parameters and layers are initialized. The parameters for the decoder are defined as follows. Output dim is the number of possible output values, or the target vocabulary length. Emb_dim is the dimensionality of the embedding layer. Hid_dim is the dimensionality of the hidden state in the LSTM. N layers is the number of layers in the LSTM. Dropout is the dropout probability. The decoder includes an embedding layer that maps the output values to dense vectors of size emb_dim, an LSTM layer that takes the embedded input and produces hidden states of size hid_dim. Next, a linear layer maps the LSTM output to the output dimension, output_dim. Finally, a softmax activation function is applied to the output, generating a probability distribution over the output values. To construct the sequence-to-sequence model, define the sequence-to-sequence class, inheriting from NN module, with the encoder, decoder, device, and target vocabulary. Targ vocab as inputs. The forward method accepting source and target sequences and teacher forcing ratio manages the model's forward pass. Teacher forcing is a training technique used in sequence-to-sequence models that involves using the true or correct output sequence from the training data as input to the decoder, instead of using the previously generated output from the model itself. It boosts model training. Initialize batch size, targ len, and targ vocab size. Create output tensor to hold the decoder's predictions at each step. Extract hidden and cell states from the encoder of using the encoder, SRC, and set them as initial states for the decoder. Start the decoder with the first target sequence token. For each target sequence time step, pass the input and prior states to the decoder, saving the output tensor and outputs. Decide whether you need to apply teacher forcing at each step, using the true target token, targt, or the predicted one, output argmax1, depending on the teacher forcing ratio. Then return the outputs tensor, which includes predictions for each time step, completing the sequence-to-sequence model construction. Let's now recap what you learned. In this video, you learned that RNNs can be used to create sequence-to-sequence models that receive one sequence as input and generate another sequence as output. The encoder-decoder architectures are introduced so that the sequences do not necessarily require to be of the same length. The encoder-decoder sequence-to-sequence model works together to transform an input sequence into an output sequence. Encoder is a series of RNNs that process the input sequence individually, passing their hidden states to their next RNN. The last hidden state, context, is passed to the decoder module. The decoder module, similarly, is a series of RNNs that auto-regressively generates the translation as one token at a time. The embedding layer transforms the input token into an embedded vector, which traverses through the RNN cell to produce the hidden state. Welcome to Metrics for Evaluating the Quality of Generated Text. After watching this video, you will be able to describe the concept of perplexity, evaluate the quality of text using precision, and recall in text generation and implement evaluation metrics for generated text. Generative AI and large language models, or LLMs, are extensively used to generate texts, images, and a lot more. The measurement of their accomplishment lies in their ability to generate consistent and contextually relevant text. But how can you measure and evaluate the performance of these models accurately? This is where perplexity comes into play. It is a metric that has emerged as a precious tool for evaluating the efficiency of LLMs and Gen AI models. Let's take a look at an illustration. Consider the phrase, "I love to travel." Given a text corpus, there are tools to assign precise probabilities to whole sequences of words, effectively gauging the likelihood of any specific sequence occurring within the data. These probabilities mirror true values or Y labels in a classification task. As you parse the sentence, note that the conditional probability becomes more complex. Each word's probability takes into account the cumulative context provided by all preceding words. For instance, travel isn't considered alone, but as part of the chain "I love to," reflecting its dependence on what has already been said. This principle is universally applicable to sequences of any length, symbolized by the variable omega t to represent each word. It is crucial to understand that this is a simplified model. Actual probability computations for a complete corpus are significantly more elaborate. Denote this inferred probability as P. To evaluate the performance of your language model, or LM, you must compare its output against the actual likelihood, typically derived from validation data. Your LM calculates the probability of observing a particular sequence as illustrated here. It approximates the true probability distribution, exemplified by a bigram model sourced from a neural network, where theta represents the model parameters and the first term is 1. This estimated probability is known as the likelihood, which is symbolized as Q. The term Q is essential for gauging the fidelity of your LM to the underlying data it aims to represent. This is closely related to the loss function. In Perplexity, you can employ cross-entropy loss to measure the discrepancy between the predicted and actual distribution. For demonstration, a simplified scenario is presented with a single variable. As your predicted distribution converges with the true distribution, the cross-entropy loss diminishes. Ideally, when the two distributions coincide perfectly, the cross-entropy loss reaches 0, indicating no difference between them. Consequently, as the predicted distribution more closely approximates the true distribution, you'll observe a decrease in the cross-entropy loss, signifying an improvement in your model's accuracy. In the context of language modeling, perplexity can be seen as a measure of how surprised or uncertain the model is when predicting the next word in a sequence. Perplexity is calculated as an exponent of the loss obtained from the model. For each sequence, perplexity is calculated from the average loss of all its tokens. By applying the exponential function to the average cross-entropy loss, you can obtain perplexity. Exponentiating the loss has the effect of undoing the logarithm and transforming the value back into a more interpretable space. Let's look at an example to see how to calculate perplexity. Suppose you have another model with less accurate predictions, as shown. By applying the exponential function to the new loss value, you get 142.6. You can see that the exponential function makes the difference clearer. Lower perplexity values indicate better performance. Perplexity provides an overall measure of model performance but doesn't capture the nuances of generated text quality. Perplexity is usually used only to determine how well a model has learned the training set. Other metrics like blue, rouge, and more are used on the test set to measure test performance. There are also metrics that measure the similarity between the generated text and a set of references based on n-gram matching. This is helpful in evaluating the quality of the generated text. And when there is more than one valid generated text, for example, in the translation task, you can compare the generated translation with different versions of the translation. This illustration shows how matching n-grams are counted by comparing a hypothesis sequence with a reference sequence. The is matched, so the unigram count increases to 1. Big is not matched, so the unigram count remains 1. Cat is matched, so the unigram count increments to 2. Sitting is not matched, so the unigram count stays at 2. On is matched, so the unigram count goes to 3. The is matched, so the unigram count increases to 4. Also, on the is the first matched bigram, so the bigram count increases to 1. Rug is not matched, so the unigram count remains 4 and the bigram count remains 1. In machine translation, precision and recall are used to evaluate the quality of the translated text compared to the reference or target translation. Precision in machine translation measures the accuracy of the generated translation. Count match is the number of matching n-grams between the generated translation and the reference translation, and count generated is the total number of n-grams in the generated translation. Recall that machine translation measures the completeness of the generated translation. It emphasizes the coverage of the important content from the reference translation. Count reference is the total number of n-grams in the reference translation. F1 score is also a harmonic mean of precision and recall that is used to judge the performance of a model based on them. In the field of natural language processing, or NLP, there are several popular libraries providing implementations of various evaluation metrics. Some of the commonly used libraries for NLP evaluation metrics are NLTK library, which includes Blue and Meteor. You can also see their initialization codes. Then you have the PyTorch library with perplexity and cross-entropy loss. There are other libraries as well that include Blue and Rouge. Let's look at a use case of the NLTK library that calculates the Blue score for a generated translation. First, define a function that creates references and hypothesis lists in the format that sentence blue accepts, calculates the blue score for them, and returns the score. Then, create an array of references. Finally, call the function to calculate the blue score for the hypothesis sentence that can be the model's generated translation. Let's now recap what you learned. In this video, you learned that perplexity is a metric and a precious tool for evaluating the efficiency of LLMs and Gen AI models. In perplexity, you can employ cross-entropy loss to measure the discrepancy between the predicted and actual distribution. Perplexity is calculated as an exponent of the loss obtained from the model. Perplexity provides an overall measure of model performance, but doesn't capture the nuances of generated text quality. In machine translation, precision measures the accuracy of the generated translation, whereas recall measures the completeness of the generated translation. F1 score is a harmonic mean of precision and recall that is used to judge the performance of a model based on them. In NLP, there are several popular libraries that provide implementations of various evaluation metrics, such as NLTK and PyTorch libraries.